Hello, hello.
Hello.
Johanna, I'm gonna do a midterm review session for one of my classes, 9 to 10 p.m. But 10 to 11 p.m. I will answer like ochem 1 questions. Is that okay? Yeah. Okay. So let's start with 118c. Um, let's see here. I think Camilla had specific questions, so I'll answer her questions first. Let me go check the questions here. Let's see questions. Uh, okay. Send you the question, but this is confused on. Okay. This is chapter 24, farahat. Let me import this. Actually, let me just import chapter 22, 23, 24. So we can go over them. Okay. And let's prioritize the practice problems on Canvas that he posted. Let's see, practice problems. Chapter 22. Practice, send a copy. Import this one. Okay. Let's see. Downloading. It's downloading right now. Okay. Um, okay. Add, import, done. 23. Send a copy. Import. Yeah, it's taking a while to download it now. But for now, let me know what problems you guys want to go over for 118c. And then I can go over those problems or any topic that you guys want to go over, and I can go over those topics as well. Yeah. While I import these documents in. So, downloading chapter 24. Okay. Done. Let me share my screen now. Share screen. Start. Okay. Is my audio okay? Am I cutting off?
Your audio is good.
Uh-huh. Okay, okay. That's good. Let's see. Okay, so this question here, question 8. Which of the following would be a reducing sugar and can react with a silver ion or do mutant rotation? So let's go over the concept of what a reducing sugar is and what a non-reducing sugar is. A reducing sugar is going to be, let's say, the cyclic version of the sugar. The anomeric carbon will be a hemiacetal. Right? So let's say we have this sugar here, right? Where this carbon to the right of the oxygen is the anomeric carbon. If we focus on the anomeric alcohol, right? I mean the anomeric carbon, we see that this anomeric carbon is a hemiacetal, making this a reducing sugar. And back in 118b, we learned that a hemiacetal is when we have a carbon attached to one OH group and one OR group. So half of the groups is an alcohol, the other half is an OR group. It's half of an acetal, right? Whereas a non-reducing sugar is going to be when the anomeric carbon is an acetal. Right, so let's get rid of this. The anomeric carbon will be an acetal. Acetal. So an example would be something like this, where let's say we have this same sugar, but instead of having an alcohol on the anomeric carbon, we're going to have a OR group, like let's say OCH3, right? We see that this acetal here has two OR groups, like that, making this a full acetal, non-reducing sugar. It cannot do middle rotation. It cannot do any other reaction, right? Normal linear Fischer rejection sugars like D-glucose, D-mannose, D-galactose, or D-fructose even, if they can cyclize, they are reducing sugars. Anything that can cyclize are reducing sugars. So the regular linear Fischer rejections of sugars here are reducing sugars. So that's the reducing sugar right there. Something that is not a reducing sugar, right? Not a reducing sugar that is in Fischer rejection would be something like this, where we have a Fischer rejection, but there's no carbonyl. There's no anomeric carbon, so we cannot cyclize the ring. We cannot close the ring. That is not a reducing sugar, right? But you'll most likely see this in rings, cycles. So at the anomeric carbon, if it's a hemiacetal, reducing sugar. If at the anomeric carbon it's a acetal, where the carbon is attached to two OR groups, OR, that's a non-reducing sugar. A sneaky example would be something like this, where you have a disaccharide, right? Where the glycosidic bond is going to be, yeah, let me just define what a glycosidic bond for you guys to make it easier. Right, so glycoside bond is going to be the bond between the anomeric carbon and oxygen, and OR group. And it has to be an OR group to be considered a glycosidic bond. So we see that this is the anomeric carbon of this sugar, and this right here is the the glycoside bond, right? Which is the bond between the anomeric carbon and the OR group here. This specifically is going to be called a 1,4-beta glycoside bond, right? The reason why it's a 1,4-beta glycoside bond is because the official nomenclature for sugars is something like this, where the anomeric carbon is going to be number 1, this is going to be number 2, 3, 4, 5, and this carbon of the CH2 is 6 right there. It's the same for the other sugar as well. So that's 1, 2, 3, 4, 5, 6. We see that this glycoside bond here is connecting this one sugar at carbon 1 to the other sugar at carbon 4. That's why we get the 1,4 right there. And this is a beta glycoside bond because we see that this glycoside bond here is facing up, which is on the same side as the CH2OH, cis, right? So if it's facing up with the same side as the CH2OH, then that is considered the beta glycoside bond, right? Like that. So that's how we determine the glycoside name and what a reducing sugar is versus what a non-reducing sugar is. So if we go back to the problem here, number 8, we see that these carbons here in red are the anomeric carbons, right? Those anomeric carbons here has an OR group, so this is a non-reducing sugar. So A is not the right answer. B, this is the anomeric carbon, OR group, acetal, not the right answer. C, this is the sneaky example here. This is an anomeric carbon, OR group. So this part of the molecule here is not a reducing sugar. But we have another sugar here with that anomeric carbon, which is a hemiacetal. And if we have a hemiacetal on the anomeric carbon, then that is considered a reducing sugar. Right, so this works, making C the right answer. D is not the right answer because this Fischer projection here has no carbonyl, no anomeric carbon, so we cannot close the ring, not a sugar. E right here, that's the anomeric carbon. This is the anomeric carbon. OR, there's no OH. So this is like acetal on both anomeric carbons, making this a non-reducing sugar. Did that make sense, Camilla?
Oh wait, there's hella people here.
Clarify, it can't do the ring if it doesn't have a carbonyl, right?
Yeah, it cannot close it to a ring if it doesn't have a carbonyl. It has to have a carbonyl in order to close the ring. Like in aldehyde, you'll see CHO. For ketones, you'll see a carbonyl and carbonyl.
So first we would have to see one if it has a carbonyl and two if it has a hemiacetal or
the carbonyl would be in the linear Fischer projection. So this is the linear Fischer projection here. All you're looking for if there's a carbonyl, right? For the hemiacetal, that's when you look for when it's a cyclic sugar, when it's a closed ring ready, right? Like the rest of the answer choices here are closed sugars, like ring sugars, cyclic sugars, right? And in cyclic sugars, to tell if it's a reducing or non-reducing sugar, we see that at the anomeric carbon, if it's a hemiacetal, then it's a reducing sugar. If it's an acetal, then it's a non-reducing sugar, right? You look at the hemiacetal versus acetal at the anomeric carbon on the cyclic sugars. For linear sugars, then you look for if there's a carbonyl or not for linear sugars. Okay. Any questions on this? Okay. Let's see. What we'll do is I'll go back to your other questions, Camilla, but I'll alternate 118c questions like other people, and then I'll go back to your questions, Camilla. Is that okay?
You're all good. Thank you.
Yeah, no problem. Okay, if not, like if anyone does have any questions, then we'll just continue with your questions. But for now, do you guys have any questions on any of the practice for 118c? Okay, so if not, let's move on to Camilla's next question, which is going to be question number 10. Okay, which of the following would you expect to exhibit middle rotation? So we went over this in the last problem. Something that can do middle rotation are reducing sugars, right? So let's look at A. A is a linear sugar, right? And what do we have to look for linear sugars to tell if it's a reducing sugar or not?
Brooks in here.
Right. Like, is this considered a sugar at all in the first place? This Fischer projection? Yeah. So if there's no carbonyl, like no CHO or no ketone, then this is not a sugar, not a sugar. So that's not the answer. Let's look at B. This is the anomeric carbon on the cyclic sugar. That is an acetal, right? Because we have an OR group. An acetal on the anomeric carbon is a non-reducing sugar. So B is not the right answer. For C, we have an anomeric carbon here, where both anomeric carbons have an OR group. Wait, no, that's not the OR group. OR group, making that a non-reducing sugar. So it's not C. Let's look at D here. Anomeric carbon. Both anomeric carbons here have an OR group. So that's a non-reducing sugar. So that's not the answer. For E here, this is the anomeric carbon. OR group. So this part of the molecule here is a non-reducing sugar. But if we look at this anomeric carbon right here, that is a hemiacetal, where we have one OH group, one OR group, making this a reducing sugar, which can do mutual rotation. So the answer here is E. Right. Okay. Yes. Any questions on this? Okay. Let's see. Next one was number 11.
Oh, I just had a question on the second photo that I sent you. Like how they got the 1,2 glycoside, the linkage. Like
Oh,
I
like
didn't know how that carbon was number 2.
oh, like this last question that you sent me here, like the most recent picture.
Yeah.
Okay, yeah. So
Thank you.
yeah, no problem. This is from Farahat's exercise, right? I think.
Yes.
Okay. So what he drew was this right here. This rotated sugar. CH2OH. OH. Okay. So let's look at this pyranose first, the 6-membered ring. For the pyranose, the anomeric carbon is gonna be the number 1 carbon for aldoses. And first we have to determine like if this came from an aldose or ketose. So let me actually I'll go back to this quite later, but I have to explain like how we close the ring for aldoses and ketoses, right? So for an aldose, like let's say D-glucose, for example, the Fisher projection is going to be this. Right? And we know this is a D sugar because the alcohol on the last chiral center here is on the right side. And there's a lot of D sugars. There's like D mannose, D galactose, D like fructose even, where a D sugar is when we have an alcohol on the right side of the last chiral center, that carbon right there. This is the specific configuration for D-glucose, and the way that you could like remember it is this like hand trick right here. Use your right hand. The 4 horizontal bonds in the middle here are going to be your 4 fingers, and where the alcohol is landing at, then that's where the direction of your finger is going to go to. So the second carbon here is going to be going to the right, and then it's going to be like this, right? Where the second finger, the middle finger, is going to be to the left, and then the ring and index finger is going to be to the right. So this is D-glucose right here. The specific configuration of D-glucose, right? And when we do the official numbering system for sugars, our number 1 carbon is going to be the top carbon. 1, 2, 3, 4, 5, 6, like that. So this is the official nomenclature, how we number it. But when I cyclize the ring, when I close the ring, I won't number it like that, right? But just know that this is the official correct way to number the sugar. So whenever you see a CHO, that is an aldehyde. So I'm going to draw that CHO out more explicitly to show you guys that that is an aldehyde. Right. So this carbonyl carbon here is electrophilic because it has a partial positive charge. So I'm going to make that my number 1 atom. If I close the ring, I want to make a 6-membered ring. So I'm going to go down 2, 3, 4, 5, 6, right there, right? This carbon here cannot be my atom 6 because that carbon cannot be the nucleophile. It cannot attack that carbonyl carbon right there. It has no electrons to attack that carbonyl carbon. it cannot be this hydrogen because that hydrogen also has no electrons that it could use to attack. But this oxygen right here to the right has pairs of electrons that it could use to attack that carbonyl carbon and make a six-membered ring, right? So the number system in red here is not how we name sugars officially. This is just how I'm going to close the ring to make a six-membered ring, right? But before I close the ring, I want my numbering system to go straight down. So right now it's going 1, 2, 3, 4, 5, and then it tilts to the right at the very end. So to make it go straight down, I'm going to rotate these three groups right here, the OH, the CH2OH, and hydrogen. By rotating that sigma bond right there, the single bond, keeping everything on the top stationary, still nothing will change to that group. Rotate the alcohol clockwise to the right where the CH2OH is, forcing the CH2OH to where the hydrogen is, which forces the hydrogen to where the OH is, right? So redrawing everything, that last cross center here will have the OH at the bottom, the CH2OH at the left side where I rotated it there, and then the hydrogen to the right side where I forced the hydrogen to where the alcohol was. Everything else, copy and paste, right? Nothing changed to these other carbons here. Copy, paste, copy, paste, copy, paste. Right? The reason why I did this is because now that allows my numbering system to go straight down. 1, 2, 3, 4, 5, 6. Right? And this is a thing that you have to know here, and I'll show you why. Everything on the right side of the Fisher projection is gonna go down. Right? It's gonna have a direction of going down. Everything on the left side of the Fisher projection is gonna go up. And the way that this can make more sense is that think of my arm right here as the vertical line of the Fisher projection. I'm going to topple it 90 degrees to the right, forcing everything to go horizontal like that. So if I do that, the aldehyde is going to be right here, the OH is going to be right here, and then the four groups are going to be right here, right? Where this is going to be 1, 2, 3, 4, 5, 6, right? Now let's look at carbon 2. If you look at the alcohol on carbon 2, that is going to the right side, like it's attached at the right side. If I topple my hand clockwise 90 degrees, it's going to go down, right? So everything on the right side here is going to go down when I topple it 90 degrees clockwise. Everything on the left side is going to go up when I topple it sideways 90 degrees like that. So everything on the right side down, OH, H, OH, H. Everything on the left side up, H, OH, H. And then at carbon 5 right here, the thing that's going up is a CH2OH. And I'm going to represent that CH2OH like this, right? Where this is the CH2 right here. Now, once I have that, I'm going to have this alcohol attack that carbon right there, pop the one onto the oxygen, and close the ring. I'm going to draw in Haworth projection, which is going to have this format right here, right? Where this is going to be 1, 2, 3, 4, 5, 6. So after some proton transfer steps, like deprotonating the oxygen here to get rid of the hydrogen and protonating the O- here to get the OH, I'm going to attach the groups here now. I'm going to go back to carbon 1, but let's look at carbon 2. We see that carbon 2 is going down, so I'm going to make that go down. Carbon 3 is going up, so that's going to go up. Carbon 4 is down, so I'm going to make that go down. Carbon 5 is up, so I'm going to make that go up right there. Right. Now, carbon 1 right here, we see that the electrophilic carbon that got attacked is an sp2 carbon that is flat and planar. Right? So that means that this OH here could have attacked on the bottom side or the top side, giving us two different products. The OH could have been going down at that carbon, or it could have been, went up at that carbon, right? Because of the flat geometry that it had, where the nucleophile here could have attacked on the bottom side or the top side, giving us two different products at that carbon right there. And this is what we call like anomers of each other. These are two different anomers, right? Which is why this carbon here is the anomeric carbon, because it leads to two different anomers. To tell like the difference between an alpha anomer and beta anomer, locate the anomeric carbon, which is that carbon 1 right there. Find the anomeric alcohol and the CH2OH on the other side of the ring. Anomeric alcohol, CH2OH on the other side of the ring. If they are trans to each other, right, like we see this anomeric alcohol is going down, the CH2OH is going up, then this is the alpha anomer. If they are cis to each other, where we see this anomeric alcohol is going up, this CH2OH is going up, This is the beta anomer. Right. So if we want to convert this into a chair conformer, this is the base structure of a chair conformer for sugars, where this is going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Everything in Haworth's projection are going to have axial bonds. So they're either going to go up or down only. There's no equatorial bonds. Everything in Haworth's projection is either going to go up or down axial, right? But that's just a projection. The more accurate projection is the chair conformation, right? Where there's axial and equatorial bonds. So the axial and equatorial bonds in this chair conformation will always be fixed. You cannot change it. It's always going to be a constant, right? So the way that I remember this is that I always start with the axial bonds, starting at the left topmost carbon. That's going to go up. If you go to the next carbon, it's going to alternate going down, right? So it's going to have like up, down, up, down. And if that was a carbon, that would go up, and then the next one would go down, right? So up, down, up, down. If this was a carbon, up, next one would go down. So those are all the axial bonds right there, right? So now the equatorial bonds would be in the opposite direction as the axial bond. So if we look at this carbon right here, carbon 4, we see the axial bond is going up. That means that the equatorial bond has to go in the opposite direction, going down. But the direction that it goes to is very specific. It has to be parallel to the second bond, right? So if you look at this carbon here, ignore that first bond. So if this was like a free response question and he makes you to draw this chair for some reason, this is how you would draw the equatorial bonds. Ignore the first bond. Look at the next bond, which are going to be these bonds right here. The equatorial bond is going to be parallel to those bonds. So if it's going down, it has to go down that direction right there. Parallel to the bonds that I circled. Parallel to the second bond. Right? So if we look at the next carbon right here, carbon 3, we see that the axial is going down. That means that the equatorial would have to go up parallel to the second bond. So ignore the first bonds, circle the second bonds. So the equatorial bond will have to go up like that, right? In the same direction as the second bond. So if we do the same for the other carbons, we would get this directions for the other equatorial bonds, right? So do the same for the other one, up, down, up, down, up, down, and then equatorial, like that, right? So now all we have to do now is just translate whatever was in the Haworth projection into the chair conformer. We see that at carbon 2, right, the alcohol is going down. You never change the direction of the group. So in the chair conformer, at carbon 2, that alcohol is also going to go down. But we see here the bond that is going down is the equatorial bond, right? So that means the OH on carbon 2 is going to be equatorial, making the hydrogen axial, like that. If we look at carbon 3 right here, we see that the OH is going up, right? But the bond here going up is the equatorial bond, not the axial bond. So a lot of students get this confused sometimes. They see axial bonds on the Haworth projection, so they think that all of these groups here would also be axial on the chair conformer, but that's not the case, right? We only maintain the direction. The direction is the one that matters the most, because the chair conformation has both axial and equatorial bonds. So if you translate the Haworth projection into a chair conformer, all we have to worry about is the direction, right? So carbon 2 here, we see the alcohol is going down. The bond going down here is alcohol. It's equatorial, right? Carbon 3, the alcohol is going up, and the bond that's going up here is equatorial. So the OH would also have to be equatorial here. Carbon 4, the down bond is equatorial, so it's that. Do the same for the other ones. Carbon 5, the CH2OH is going up. The bond going up in carbon 5 is the equatorial bond, OH, like that. And if we're looking at the alpha carbon, the OH is going down. So the bond that is going down at carbon 1 is the axial bond right there, right? So let's just do the same for the beta anomer, like that. Any questions on this? Am I moving too fast for here? Right. Okay. So what you'll notice is that if we use D-glucose, every atom besides the NMR carbon, every group besides hydrogen is equatorial. So that's why you might hear glucose as the all equatorial sugar, right? Because every group here besides the NMR carbon is equatorial, right? If you look at the beta NMR, then every group would be equatorial, 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 equatorial. Okay. So that's how we close the ring. And that's how it would look like for D glucose. D fructose here, like let's say closing ketose is different, right? Because if I have D fructose like this, 1, 2, 3, and this is going to be OH, 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 H, H, H. So I'm gonna number it officially where the number 1 atom is at the top carbon right there. 1, 2, 3, 4, 5, 6, like that. Right, 6 carbon sugar, where the anomeric carbon here is now at carbon 2 for ketosis. Right, but when I close the ring, I'm gonna start my number 1 atom at the anomeric carbon, right, just to show the ring closing and the groups attached to it. But if you see like C1, C2, C3, C4, C5, C6, then they're referring to this green official nomenclature of the sugar right here. The one in red is just how I close the ring, where I start my number 1 atom at the electrophilic carbon. And then if I want to make a 5-membered ring, let's say, I'm going to go down 1, 2, 3, 4. This carbon here cannot be my number 5 atom because that carbon cannot be the electrophile. My number 5 atom has to be this OH here at the side, right? So we do the same trick. We have to make the numbering system to go straight down. So we're going to rotate these 3 groups. Just stop me when this doesn't make sense because we went over this process already. I'm just going to speed up the process here. Once I rotate those 3 groups, the OH is going to go down. CH2OH is going to go to the left. H is going to go to the right. Everything else copy and paste. Right, now our number system, 1, 2, 3, 4, 5 is going straight down. We already know that everything on the right side is going down. Everything on the left side is going up, right, when we topple the thing. And we only have to do that topple thing 1 time, and then once we see it, then we don't have to do it again. So when I close the ring, the Haworth projection for a 5-membered ring is going to be like this, where oxygen is in the middle. And this is going to be 1, 2, 3, 4, 5, like that, right? Where this bond right here between 1 and 5 is the new bond when the alcohol attacks that carbonyl carbon right there, right? Where this is the anomeric carbon, that's the anomeric carbon. So that means that when that anomeric carbon gets attacked, the OH could have been down or up. And those are our 2 different anomers right there. So now we see that at carbon 2, the OH is going up. So I'm going to make that go up right there. At carbon 3, OH is going down. So I'm going to make that go down right there. At carbon 4, CH2OH is going up. So I'm going to make that go up right there. Right. But look at the anomeric carbon right here. The anomeric carbon here not only has the carbonyl that got converted into an alcohol, but it also has a CH2OH. So if the OH went down, that forces the CH2OH to go up, right? So if the OH on the anomeric carbon went up, that forces the CH2OH to go down. Everything else is copy and paste because everything else does not change.
Brian, I had a question.
Yeah.
So for alpha and beta,
right,
if on the anomeric carbon, if the OH is pointed down and the CH2OH is pointed up, that would be alpha. But say if the I know it's trans, but say that if like you flopped it and like the CH2 was pointed down and the OH is pointed up, would that also be alpha?
Yeah, that would also be alpha. That's correct.
So you could just flop them and it doesn't matter. It doesn't always have to be pointed up and pointed down. You could flop them. Okay, thank you.
Yeah, you can flop them. And this would come from like the L sugar. But L sugars are not that common. D sugars are more common. So you'll most likely see CH2OH at the top. But for some reason, if he tries to be tricky and add a like tricky problem, if you see something like that, then that would be considered a trans alpha anomer still. Right.
Oh, you're saying the L sugar and the S sugar is where it's on the opposite
Yeah, the L
side.
sugar
Okay,
is
okay.
when the CH2OH is going down and the OH would go up for alpha NMR. Right?
Okay, okay. Thank you.
Yeah, no problem. Yeah, Xinyan, you had a question?
Yeah, I think you can also make like pyranos with ketones, right?
Yeah, you can also make pyranos with ketones as well. A 6-membered ring.
When do you know
Uh-huh.
that you have to make a pyranose, or when do you know you have to make a furanose?
Yeah, so to know if when you spontaneously close the ring in acidic conditions, it's gonna make both, like in major amounts. So if this was a predicted product problem, you would have to draw both the pyranose and furanose products, both the alpha and beta NMR. So you're gonna have 4 different products. Right?
Okay.
The alpha and beta NMR for both the pyranose and furanose. But for this question here that Camilla sent earlier, this right here, they gave the furanose form because we see the 5-membered ring right there.
Okay.
Right. And do you guys want me to go over closing the ketose and like to make the pyranose as well, or do you guys want to move on to a different concept after this? Let's see. Right, because I don't know if closing, I don't know if this will be an exam, but let's just go over this first. So if the anomeric alcohol and the CH2OH are cis to each other, going on the same side, then that is going to be the beta anomer. Right. Okay, so the important thing that I wanted you guys to know here is that the red numbering system is how I close the ring. The actual nomenclature here is that this is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, right? For ketosis, the anomeric carbon is carbon 2, right? So now if we go back to the problem that Camilla sent right here, this right here is the anomeric carbon, right? And we know that this sugar came from a ketose because if you see a CH2OH and an OH or OR group on the same carbon next to oxygen, that's the anomeric carbon. And we said earlier that the anomeric carbon is carbon 2, where the CH2OH is carbon 1 right there. So that's 1, 2, 3, 4, 5, 6, right? For the pyranose, this is going to be coming from an aldose because this is the anomeric carbon from the pyranose, where the aldose only has OR group or OH group and a hydrogen, right? So the difference between an aldose and ketose in the cyclic form is that an aldose will have a hydrogen at the anomeric carbon, a ketose will have a CH2OH at the anomeric carbon, right? So this right here came from a ketose. This right here came from an aldose because at the anomeric carbon, it has a hydrogen for aldose. At the anomeric carbon, the ketose has a CH2OH, where the anomeric carbon is 1 for the aldose, 2, 3, 4, 5, 6 for the official nomenclature for the ring. Right, so we see that this is a 1, 2 alpha glycoside bond. Right, because we see that at this anomeric carbon right here, the OR group is trans to the CH2OH, so that's the alpha glycoside bond. And it's 1, 2 because it's connecting the 2 sugars at carbons 1 and 2 right there. Did that make sense, Camilla?
Yes. For finding out if it's alpha or beta, would it ever be that one molecule is trans to the bond and the other one cis, or will they always add up?
Yeah, so this glycoside bond here that I'm referring to is going to be this bond right there, right? But if you look at this OR group right here and this OR group right there, notice how they're cis to each other.
Yes.
Yeah, so that like right there, the glycoside bond would be beta, right? Beta.
Oh, okay. I see.
Right.
Thank you.
But this glycoside bond here is alpha, right? And the glycoside bond is between an anomeric carbon and an OR group, right? This is alpha because this is trans to the CH2OH right there.
Okay, I see. Thank you.
Yep, no problem. It's just like oriented differently because he rotated it and he like kind of flip-flopped the NMR carbon, because you're used to seeing the NMR carbon at the right carbon, but the NMR carbon is right here for the sugar here. Right. Okay. If it was a ketopyranose and an aldose, how would you tell the difference? Yeah. So to tell the difference between a ketopyranose and the aldose, for an aldose, if you close the ring, you're gonna have this right here. Right, something like this. If you close ketose and you make a pyranose, you're gonna have something like this. Let's say we have something like that. Right. The difference is that for the ketose, you will have a CH2OH, and then for for an aldose, you have that CH2OH. For a ketose, you will have 2 hydrogens. Right. Up, down, up, down, up, down. Yeah. 1, 2. There's no CH2OH at this carbon here. And this is when you close the ring from a ketose to make a pyranose. Right. So let's say we have D-fructose right here. Where this is going to be 1, 2, 3, 4. This is not the official nomenclature. This is just how I'm closing the ring. If I want to make a 6-membered ring, this is going to be 5. And then this oxygen here is going to be 6. Right? But I'm going to redraw this out like this. Where the CH2OH, I'm going to expand it into the Fischer projection. Right? This C of the CH2 right here is that C of the CH2 right here. So this CH2OH is that whole CH2OH. I just expanded this CH2OH into that CH2OH right there to allow us to see the number system when I close the ring to go straight down, right? Where we see that at carbon 5, there's 2 hydrogens on carbon 5, 2 hydrogens on carbon 5, like that. Yeah. Okay. Let's see. I don't really have any revisions, but could you please go over nomenclature for chapter 22, 23, 24? Yeah, so nomenclature is my weak area in ochem. I didn't really study nomenclature that much. So like we could go over like reactions, mechanisms, synthesis, acid-based stuff, conceptual questions, but nomenclature, the IUPAC stuff, like I'm not too strong with that.
Yeah, I think it's just memorization, to be honest.
Yeah. You know the rules and practice a lot with that nomenclature. Yeah. All right. Okay, let's see. Do you guys have any topics that you guys want to go over, or any practice problems? Or any questions that we went over?
Can we go over the different oxidizing agents? So I know that he went over like stronger oxidizing agents like the nitro and the one with the iodine. And then there was like the weaker one with NaBH4, which was able to like reduce both sorry, it was able to reduce like these 2 molecules.
Yeah, for
one was
sugars?
like one was like with the ketone and the other one was just without primary alcohols. So I was kind of wondering if we could go over like oxidation reactions.
Yeah. Let's go over oxidation reactions. Okay. Okay.
Also, he said that he was like from one of his lectures, I don't know like how true this is going to be, but he was like talking about this one synthesis problem. And he was like, you will see this on the exam. So I was like, maybe if we could go over that synthesis problem too.
Yeah. Can you send me that synthesis problem?
Yeah, through the chat here?
Yeah, or
okay.
Oh yeah, you can send a file here on Zoom now. What the heck? Yeah, send it to the chat. Yeah.
Okay, I'll do that.
Yeah. Okay, yeah. So there's gonna be 1, 2, 3, 4 different types of oxidation reactions I want you guys to know for chapter 24. Okay. And after that, I'll go over that synthesis problem, and then we'll end the review session for 118c, 9 to 10 p.m. And then 10 to 11, we'll do 118a. And if Johanna's to her ochem 1 class for her school. Okay. Yes. So sugars, oxidation, we can oxidize both an aldose and a ketose to aldonic acid. Right. So what that means is that let's say I have with Fehling's reagent, or Tollen's reagent. Oh, what? Reagent. Okay. So let's say that we have this D-glucose, my favorite sugar. 2, 3, 4. And then you see any of these reagents here. Fehling's reagent, I'm going to abbreviate that as Fa, is going to be copper, OH minus, water. Tollen's reagent, I'm going to abbreviate that as, let's see, or Tollen's reagent, Ta. You're going to see silver, nitrate, NH3, and water. You might just see a silver ion. Any of those like ions like copper, silver, and aldose will be converted into gluconic acid, where we're going to oxidize this aldehyde here into the carboxylic acid. So I'm just going to assume acid workup here, where the CO2H is the carboxylic acid. Right? The bottom CH2OH does not get oxidized. Think of this as a weak oxidizing agent. It's a weak oxidizing agent because it only oxidizes the top carbon. Right? So I don't know how strict farahat is, but for leavens, if there's no acid workup step here, the answer would be the carboxylate, right? Something like this, where we have a deprotonated carboxylic acid. But if he assumes acid workup like Helix does, like H3O plus there, then the final answer would be this neutral carboxylic acid. Right? We're just oxidizing this top carbonyl here into a carboxylic acid right there. Right? That's the case with an aldose. If we had a ketose, for example, let's say this top carbon here is a CH2OH, and the second carbon here is the carbonyl carbon, the anomeric carbon, and we use the same kind of reagents, Fehling's reagent or Tollen's reagent, a weak oxidizing agent. We're gonna oxidize the top carbon into a carboxylic acid, assuming acid workup. Right, and that's it for this oxidation reaction. CH2OH. Okay, so now the next one I want you guys to know is weak oxidation with Br2 and water. And the most important thing about this reaction is that this only works with aldoses. Only works with aldoses. So if you see this reaction with the ketose, the answer is going to be no reaction, or in farahat words, there is no significant amount of product formed. If we have, let's bring in that sugar aldose, and we react it with Br2 and water. Because this is a weak oxidizing agent, we're only going to oxidize the top carbon, the CH2O at the top, into a carboxylic acid, not the bottom carbon, right? If you see a ketose trying to react with Br2 and water, there's going to be no reaction, no significant amount of reaction formed. Okay. Now, the other oxidation reaction I want you guys to know is the oxidation with a strong oxidizing reagent. which is HNO3 in water, right? Strong oxidation with HNO3 and water. Okay, so that's going to oxidize both the top and bottom carbon into carboxylic acids. So let's say we have both an aldose and a ketose, because this strong oxidizing agent here will work with both an aldose and a ketose. Okay, so this first reaction here is going to be like HNO3, water. You might see some temperature, like 60 degrees Celsius, HNO3, water, 60 degrees Celsius. Since this is a strong oxidizing agent, we're going to fully oxidize the top and bottom carbon into carboxylic acids. Right? Strong oxidizing agent. Works for both aldose and ketose. Okay. Same for the ketose here. We still have a carbon at the second carbon, so that stays there. Everything else copy and paste, except the last carbon. Last carbon also gets oxidized because this is a strong oxidizing agent. Right, like that. Okay. Okay. So I'll summarize these reagents at the end. I know this is like a lot of reagents, but I will summarize it at the end for you guys. So the last oxidizing agent I want you guys to know is oxidative cleavage with HIO4, which is the hardest one to think about. Cleavage in terms of the oxidation reactions, HIO4. So there's two different reactions here, aldose and ketose. And I'm going to show you the qualitative and quantitative product. Right? If you have an aldose, like D-glucose, and you react this with, I'm going to make it go down here. Let's say HIO4. The qualitative products here is going to be formic acid and formaldehyde. Right? So those are your only two qualitative products you get by oxidizing an aldose with HIO4. To figure out how much product we're going to get, the formic acid is going to come from the CHO carbonyl and number of secondary alcohols. The formaldehyde is going to come from the number of primary alcohols, right? So if we look at D-glucose here, CHO counts as 1. We have 1, 2, 3, 4 secondary alcohols, because the carbon that the alcohol is attached to attached to 2 other carbons. So this is like secondary alcohol, secondary alcohol, secondary alcohol, secondary alcohol. 4 plus 1 is 5. So we're going to have 5 formic acids, and we only have 1 primary alcohol, which is this primary alcohol here. So we're going to have only 1 formaldehyde right there. If this was a shorter sugar, let's say glyceraldehyde, and we only have 1 secondary alcohol, like that, then we will only have 2. We will only have 2 formic acids, right, coming from the carbonyl, CHO, and 1 secondary alcohol. If this was a longer sugar with like a lot of secondary alcohols, then we're gonna have more formic acids, right? Formic acid coming from the carbonyl carbon of the CHO plus the number of secondary alcohols. And aldose will always get 1 formaldehyde from that 1 primary alcohol right there. Right. For ketose, let's say we have a D-fructose here, and we oxidize that with HIO4. Our qualitative products will be the same as the aldose, formic acid, formaldehyde, but we get 1 more, CO2, carbon dioxide. Right. So to quantitatively determine how much of each we're gonna get, the formic acid is going to come from the number of secondary alcohols. The formaldehyde is going to come from the number of primary alcohols. And then the carbon dioxide is going to come from the carbonyl of the ketone, right? So we only have one carbonyl of this ketose here, so we only get one CO2. For D-fructose, we have two primary alcohols, one at the top, one at the bottom. So that means we get two formaldehydes. We have 1, 2, 3 secondary alcohols. So we're gonna have 3 formic acids. So that's how we can qualitatively and quantitatively determine the products for oxidative cleavage with HiO4 with an aldose or ketose. But make sure to know the names of these as well, because knowing Farahat and his like practice tests and exams, he will just might say like a formic acid and formaldehyde as the product, and you have to know what that looks like.
I also think that he's going to be really specific about using 5 equivalents depending on the length of the molecule.
Yeah, right. 5 equivalents versus like 3 equivalents versus 1 equivalent, and what that means, like, is it a shorter molecule, is it a longer molecule? Know that as well. Not just the qualitative like product, but also like quantitatively, like how to determine how much of each you're gonna get. That's good. Okay.
I don't know how to drop files in the chat. I'm able to screen share and then see if you're able to screenshot it, if that's okay for the one problem.
Yeah, you could screen share and I could screenshot it. But before that, let me summarize what we just went over for oxidation for sugars. Oxidation of sugars. So you know how in 118A you learned about oxidations of alcohols, like with PCC and Jones. Remember those reagents? Where PCC is the weak oxidizing reagent and Jones is a strong oxidizing agent. This set of reactions here is kind of the same thing, but in the sugar realm, right? Where there's a weak oxidizing agent and there's a strong oxidizing agent. The weak ones are going to be Tollens reagent agent and Fehling's agent, and they work on. Well, let's split this further with, let's say, which one can work with aldose and which one can work with ketose. Right. For aldose and ketose, Tollens agent would work. Fehling's reagent would work. BR2 and water would only work with aldose. For a strong oxidizing agent, HNO3 and water would work with both an aldose and ketose, which oxidizes the top and bottom carbon into carboxylic acids. And then HiO4 is just like its own category that does like this weird thing, splitting everything right here. Right, they make 1 carbon molecules. All of these molecules here, all of the products here are 1 carbon products. Right. Okay. So let me stop sharing my screen, and then you can share your screen, and then I could work through the synthesis column, and then we'll be done with the 118C review session today. Oh, this one here. Okay, let me screenshot this. Okay, I got it. Okay. Let's see what is going here. Let me share my screen again. Okay. Very similar one that Nasiri had. Okay. Yes. Now we get here A2003. Okay. I see. So this synthesis problem here, the key takeaway step is protecting the phenyl alcohol by converting it to a benzylic ether. And then deprotecting it with H2PDC, right? Which is going to reduce the benzylic ether back into the alcohol. Reduce benzylic ether to the alcohol. So let me explain this here. We see that we have this benzene right here with an alcohol and nitrile, CN. This right here is going to be the protecting step, which is going to convert this alcohol into a benzylic ether, right? K2CO3 here, when you see K2CO3, think of a base, right? That base is going to deprotonate that alcohol to create a phenoxide, right? A negative charge on that oxygen right there, which makes that oxygen negatively charged. And then this is going to do an SL2 reaction with that CH2, like with the bromine leaving group, kick that out, and then give us this intermediate here, this product here, right? And this is a benzylic ether because this carbon here is the benzylic carbon. That is a benzylic carbon because that carbon is coming off of the benzene ring right here, right? Now this is protected because now we could bring in some kind of base to convert this nitrile into like this thing in chapter 24, the nitrogen, like I forgot the name of that. It was like it was like amine something. Let's see. Something with the nitrogen primary means hydrazone, something like that, right? Sazone, phenosazone, right? Because the reason why we had to do that is because this reagent here would have also reacted with the OH, but we don't want the OH to be interrupted because we see in the final product here, this OH is uninterrupted, right? Nothing happens to that OH, but something did happen to the CN, which got converted into this group right here, which is from this reagent here, right? But this reagent would have reacted with the OH, so we had to protect the OH by deprotecting it first, and then doing SN2 to get this benzylic ether, and then we do this reagent to convert the nitrile into that group that we want, the hydrazone, and then once we have that, we deprotect the benzylic ether back into the alcohol by using H2PDC, reduction of benzylic ether. Right. What reagents should we look out for to protect alcohol against? Yeah, so the reagents that you want to look out for are going to be this that he gave you. And some acyl group like that. Or like some Friedel-Crafts reagent like that, AlCO3, or it doesn't have to be Friedel-Crafts acylation, it could be alkylation as well. Some strong base, like OH minus, H minus. Let me give you a similar problem here that you have to use that protecting reagent in. Right. Let's see here, chapter 22.
Can you Tell me what DMF does again, if that's okay.
Yeah. DMF is, when you see those 3 letters, think of that as an A product solvent. Right. An A product solvent that has no H bonds, and that would not interrupt the reaction. So it will not do anything in the reaction. It will not interfere. It's just there to facilitate the SN2 reaction. Right. The K2CO3 is a base that would deprotonate the alcohol to create the nucleophile. And then once you have the nucleophile, we're going to do an SN2 reaction with that that group with the good leaving group. And DMF is just an A product solvent that allows that to happen. An A product solvent. It will not do anything in the mechanism. Right. Let me find that right here. Reduction of, oh, that's was that chapter 22 or let me see. Oh, we're here. Yeah, it's right here. That synthesis file has some 118B reactions to it. So we're not gonna do that in a serial one. Let me just create one for you guys right here. Let's say we have this, and we have this, and you want to, let's say, do this. No. I'm just gonna do something else. Okay. No, that's not. Yeah, that's not gonna do that. Yeah, there's another way that you would have done that. I'm trying to do Friedel-Crafts isolation here, but if I protect the thing with the benzene group, then we're gonna have 2 different competing things. So actually, yeah, it would still work. It would still work. So let me just do it like this. Yeah, so we have this, and then we want to make this here. Right, so there's 2 ways that you could do this. I'm going to show you why this would not work. We see that we added an acyl group para to this EDG, right? This is an EDG here because it could donate electrons directly into the ring, and the first atom is partial negative charge, which is an ortho para director. So when you try to do Friedel-Crafts isolation with it, with that group in AlCO3, second step acid workup, you would expect that product, but this would not go through, right? The reason why is because the alcohol is a stronger nucleophile than a benzene ring. So when you just do those 2 reagents, what you're actually going to get is this right here, where the OH attacks the acyl group to create that ester right there. So think of this as a chapter 20 reaction, right? We have an acyl halide reacting with an alcohol. That's going to create an ester right here, right? Where we substituted this chlorine with that whole alcohol group, which is this OR group right there. So the reason why that happens is because this alcohol here is a stronger nucleophile than the benzene ring right here. So what we have to do is we have to protect the phenyl alcohol, and we could do that by doing K2CO3, this leaving group, and then DMF solvent, which is going to give us this benzylic ether. And then we could do, let's say, 1 equivalent of K2CO3. No. The acyl halide reagent, the acyl halide, AlCO3, second step acid workup, to add that acyl group to where we want it to be, ortho to the EDG, and then deprotect it with H2PDC, deprotect the benzylic alcohol ether with H2PDC. The reason why I was thinking about this could be a problem is because we have 2 benzene rings here. So when I try to do Friedel-Crafts isolation, it could react with both benzenes, but it would prefer to react with this benzene here more. Can you guys think of a reason why like the acyl group would be attached to this benzene instead?
Because the oxygen can donate electrons into it, which make it more reactive.
Yeah, this is a stronger EDG. And if you look at this carbon here, this carbon is partial positive charge because it's attached to an electronegative oxygen atom. So that would be an EWG by induction, right? So this is a more activated ring. So we're going to put the acyl group para to this position right here. And then once we have that, we could deprotect this benzoic ether with H2PDC to convert it back into the alcohol that we have right here, right? That's not the only protecting group you could do with the alcohol on the phenol group. You could have also protected it with, let's say, just like first step NaH, strong base, second step CH3Br, right? To get this ether here, OCH3, right? The H minus here, the strong base, deprotonates the alcohol to get the phenoxide ion nucleophile, which attacks that CH3, kicks out the Br to get that ether. And then you do whatever reaction you want because that ether is unreactive. And then to deprotect that ether, all you have to do is put like HX, like HBr. And that's going to convert that ether back into the alcohol like that, right? Because this is when it's an A reaction, the acid here is just going to protonate the oxygen to make that a positive charge. And then the Br minus here is just going to attack that carbon and then kick out that leaving group, giving us our alcohol back, which is our leaving group. So that's the other protecting group and deprotecting reagent you could use instead of this benzoic ether thing here, right?
Could we use thioacetal, like the little cap, and then reduce it with rainy nickel with that reaction?
Oh, right. You're thinking of this protecting group, right? Like this thioacetal thing right here with the
yeah, that
nickel.
one.
Yeah, so this one here is protecting carbonyls.
Oh, not alcohols. So.
Yeah, not alcohols, right? This was protecting carbonyls, right? And then I think if Annie's here, Chem8b, this is gonna be covered in the next midterm for Chem8b. Yeah. Okay, yeah. H3CO2. Yeah, let's get the first step, chapter 22 reaction. Yes, it's a chapter 22 reaction. So benzoic ether and reduction of benzoic ether, chapter 22. Okay. Yes. So thank you guys for coming for 118C. I'm going to now shift to ochem 1 and 118A. Good luck on the midterm on Thursday.
Thank you so much.
Thank you.
No problem. See you guys. Okay. So let's see. I'll do the H&MR problem first with Elysia, and then Kathy will answer some of your questions, and then Johanna, I'll pull up that document you sent me through email, and then we'll call it office hours. Okay. Hey Elysia.
Hi.
So let's see you H&MR. Did you send the document that you wanted to go over with the practice to the Google Drive?
Yeah, I put it under resources.
Okay.
It should be titled something. I think I said I forgot what I labeled. Interpreting H&MR.
Interpreting H&M. Oh, we're here. I see it.
Yeah.
Copy. Okay. Okay. Yes, this one. Okay. Yes, you're familiar with IR, like how to interpret IR and the functional groups present, right, for IR?
Yeah. I think I'm just really confused on the peaks and like also predicting the structure of the molecule using the
HNMR.
yes.
Yes, okay. So HNMR, there's three things that I look for. There's gonna be like the most important thing, what peaks are de-shielded versus what peaks are shielded. And then I look for the next important thing, the multiplicity or the n+1 rule to look for the number of neighbors, and then I look at the integration. Right, so let's go over that. For HNMR, the range that you can see in is going to be from 0 to 12. The more to the left side you are in the graph, that's going to be the more de-shielded region. The more to the right side you are to the spectrum, that's going to be the more shielded region. And then what this shielded and de-shielded means is that let's say that we have this hydrogen here, right? Because HNMR, they read the unique hydrogens on the molecule. That's why it's called hydrogen NMR. A shielded hydrogen is going to be a hydrogen shielded by electrons, like that, right? So that's what is shielding that hydrogen, the electrons around it. So when the HNMR like tries to read the hydrogen, it has a hard time reading it, so it appears at the right side with a lower ppm range, right? Because it cannot read that hydrogen as much since the electrons are blocking the magnet or light or whatever the HNMR uses to try to read the hydrogen, right? So that's why it has a lower ppm value. The more it's more shielded, right? Because it's shielded by the electrons, and shielded electrons tend to be attached to like non-electronegative atoms, non-electron withdrawing groups like carbon, right? This is a non-polar bond right here. Carbon is not that electronegative, so it's not going to withdraw electrons from hydrogen that much. So there's still going to be a lot of hydrogens around that hydrogen, making it shielded. But if we look at this hydrogen here attached to some electronegative atom like oxygen, nitrogen, fluorine, bromine, any electronegative atom, those electrons are going to be pulled towards the electronegative atom, making this hydrogen de-shielded, right? Because the electrons here are no longer shielding the hydrogen. So when we use the HNMR, whatever that reads the hydrogen is able to hit the hydrogen and see it and read it, making it have a higher ppm value, which is why anything to the left side is more de-shielded. So that's the concept of what de-shielded means and shielded means for HNMR. Does that make sense?
So you're saying with the shielded, our hydrogen is shielded, and it tends to be attached to a carbon versus de-shielded is the hydrogen is unshielded and it's shielding the like fluorine.
Yeah, so the hydrogen here is de-shielded, meaning that it has less electrons attached to it, and it will have less electrons attached to it if electronegative atoms or electron withdrawing groups are next to the hydrogen or directly on the hydrogen, pulling away the hydrogen's electrons, right? Because you see how here this hydrogen on the right is shielded because there's a lot of electrons attached to it, whereas the hydrogen on the left here, there's like only one electron right there. All of its electrons are being pulled by that electronegative atom like fluorine, like you said, or oxygen or nitrogen.
Oh, okay.
Right. And because it's de-shielded, it's like naked, so the HNMR is able to see it, and that's why it has a high ppm value. Whereas the shielded one is shielded by electrons. This carbon here is not electronegative enough to pull those electrons, so those electrons are still around the hydrogen. So the HNMR cannot read it as much. That's why it has a lower ppm value on the right side.
Okay, that makes sense.
Right, right. So now that's the concept of de-shielded versus shielded. Now this is what I think about when I think about HNMR. 0 to 2 is the boring region, where that's gonna be the carbon hydrogens that are regular, right? Like that are bonded to like no electronegative atoms, not next to any electronegative atom at all. 2 to 3 is gonna be the alpha region, and what I mean by that is that the hydrogen here is gonna be alpha to a double bond, right? This is the alpha carbon right here. because that's the first carbon away from the double bond. It could be an alkene. It could be a carbonyl. It could be alpha to an alkyne. Or it could even be the alkyne, terminal alkyne hydrogen itself, like this. Right. Now, 3 to 4 is when it gets more interesting, because this is when the hydrogen is attached to a carbon that is attached to an electronegative atom, X, where X could be oxygen, nitrogen, chlorine, bromine, iodine, any electronegative atom, right? This hydrogen here is more deshielded because it's attached to a carbon that is attached to an electronegative atom like that, right? 4 to 6 is going to be the alkene hydrogens. So these hydrogens here directly on the alkene hydrogen carbons, right? That's different than this hydrogen right here, because this hydrogen here is just on the alpha carbon, right? This is the alpha carbon, alpha carbon, alpha carbon, one carbon away from the alkene. But if you have a hydrogen directly on the alkene, that's going to be between 4 to 6. 6 to 9 is going to be the benzene hydrogens, the aromatic hydrogens. So if you have a benzene like that or aromatic like that, all the hydrogens there attached to the benzene directly is going to be between 6 to 9. Right, and then you're going to learn more about that in 118b with the ortho meta para position groups, but this is where the benzylic not benzylic, the phenylic hydrogens are going to be at. The hydrogens directly on the benzene ring, 6 to 9. If you see peak around 10, that's going to be the aldehyde hydrogen. If you see peak around 12, that's going to be the carboxylic acid hydrogen. Right. Now, if you see a peak around 0.5 to, let's say, 5, and you see it as like a broad peak like that, usually around 4 to 5, then that broad peak is most likely going to represent an alcohol or an amine. Right? And this amine here could be primary or secondary, most likely secondary, with a hydrogen, right? And that peak is broad because it has H bonds. Most peaks in the HNMR will be sharp like that. Right? But if you see a broad peak like this, around 0.5 to 5, then that's gonna be because we have an H bond. Like if you have an alcohol here, the H bond is between that hydrogen and oxygen. If you have an amine like this, the H bond is between this hydrogen and that nitrogen right there. And because of that H bond right there, where the H is bonded to like fluorine, oxygen, or nitrogen, that makes the peak broad on the HNMR. Right. Okay. So that's what I look out for the thing. Let's do one problem to make it more clear, and I'm gonna explain multiplicity and integration as I work through that problem, and then we can do practice more tomorrow, office hours. Right.
Okay.
So let's do one that looks crazy, which is gonna be this one here. 6 to 8. That's more of a 118b thing. I don't think you'll be tested on this for 118a.
Yeah, I'm not sure.
Yeah. Right. So let's do this one. Let's do this one. Okay. So here's my there's different ways to approach HMR problems. These are the 5 steps I do when I do HMR problems. The very first thing I do is calculate the degrees of unsaturation, right? And there's a formula for that: 2C plus 2 minus H minus X plus N all over 2. The next thing I do is look at the IR for the functional groups. And then the next thing I do is look for the HNMR for the peaks. And then the next thing I do is make fragments based on an HNMR. And the next thing I do is connect the fragments, and pray. Right. Because a lot of this is trial and error. Trial and error. Okay. So what degrees of unsaturation means is that how many double bonds or triple bonds or rings we have. If you have a double bond, that's 1 degree of unsaturation. If you have a triple bond, that's 2 degrees of unsaturation. If you have some kind of ring, like a cyclohexane, a cyclopentane, cyclobutane, or cyclopropane, that's 1 degree of unsaturation. So let's say you have a double bond and a triple bond. That's going to be 1 plus 2. You're going to have 3 degrees of unsaturation. If you have a benzene like this, how many degrees of unsaturation would you expect if you have a benzene like this? At least. Like, let's just say we have a benzene here. How many degrees of unsaturation would you expect for this benzene here?
3.
Yeah, 3 double bonds, 1, 2, 3, plus
Yeah.
1 ring.
Right.
So 3 plus 1 would be 4. If you see any benzene ring, that benzene ring will count as 4 degrees of unsaturation.
Okay.
Right. Because of the 3 double bonds, 1, 2, 3, and 1 ring. Okay. So now let's look at this one. Let's look at the chemical formula C7H4O2. If I were to calculate the degrees of unsaturation, that's going to be 2 times 7 plus 2 minus 14. Oxygen is not included in the formula, all over 2. 2 times 7 is 14. 14 plus 2 is 16. 16 minus 4 is 2. 2 divided by 2 is 1. So we have 1 degree of unsaturation, meaning that we cannot have an alkyne because an alkyne has 2 degrees of unsaturation. We could either have an alkene or a ring. Right. Now, look at the IR. What functional groups do you see present in the IR? How would you interpret this IR?
I'm a bit like, I kind of need to use my reference card for this. I'm still trying to get the hang of it.
Yeah, no worries. If you see a peak at around 3,000, that's the regular sp3 carbon hydrogen peak. So we could basically ignore that. If you see 1,500 and below, that's gonna be the single bond fingerprint region where you can like see single bond O. So for the purposes of like che118a, you could ignore that. Now if you see a sharp peak at around 1,700, this is the important peak right here. Can you remember what functional group is around 1,700? A sharp peak at around 1,700? Let's see if I have the IR chart here. Over here. There we go. Let's put it right there.
Carbonyl.
Yep, carbonyl. Carbon double bond oxygen. Carbon double bond oxygen. So we see a double bond right here. That double bond right there is going to account for our 1 degree of unsaturation. Right, so we have a carbonyl somewhere in our molecule. Right, so wait, are these the molecules that are possible for unknown H? Or like, did they give us, or are these the ones that they give us for this one here, for this problem? And then we have to choose.
I'm actually not sure. I just took this as a resource from I think Edna.
Right. If these are the options that you are going to choose, we could do process of elimination here, where we know that there's a carbonyl, so we could get rid of B. Like, I don't know if this is the key or like this is because like the way that this letter is so weird. Let me see here. Let me read the beginning here. Oh no, it's here. So they give us 1, 2, 3, 4, 5, 6, 7, 8, and 8 different IRs, and they want us to mix it up to match the structures with the IR, right? So for the problem that we've been doing, let's say these are our choices of molecules that we could choose from, which is nice because usually they don't give us choices. They make us predict the product from scratch. So these are our choices right here. We could do process of elimination by getting rid of all the ones that doesn't have a carbonyl. No carbonyl, no carbonyl, no carbonyl, no carbonyl, no carbonyl, no carbonyl. So we're left with this molecule and this molecule here. Does that make sense on why I got rid of all the other molecules there?
Yeah.
Right? Because in our IR, we see that we have a carbonyls, a sharp peak at 1700, and our two molecules here with a sharp peak at 1700 is going to be this and that. So now, like, if I want to predict the product quickly, it's going to be very simple because I see that I have an aldehyde right here, and looking at the IR right here, if we have an aldehyde, we have a sharp peak at around 2700, right? So let's look at the IR here. We do not have a sharp peak at around 2700. This is 2500, 2600, 2700. There's no sharp peak here, so there's no aldehyde. So I'm gonna get rid of this molecule here. Does that make sense? And why I get rid of that right there?
Yeah.
Okay. Another reason why I know that that's not the right answer is because how many unique hydrogens peaks would you expect here on this molecule? Let's say I draw all the hydrogens.
Well, can you repeat your question, please?
Yeah. How many unique sets of hydrogens would you expect for this molecule here? How many unique sets of hydrogens would you expect in the HNMR?
I'm not sure.
Yeah, so to figure that out, we have to see which sets of hydrogens are chemically equivalent. We see that these three hydrogens here are chemically equivalent because they have the same chemical environment. And then this one hydrogen here is like it's alone. There's no other chemical equivalent hydrogen, so that's alone right there. So there's two sets of hydrogens here.
Oh, okay. Yeah, I see that.
Right. Let's see. How many neighbors would you expect for this one hydrogen to have right here?
Well, we look at the one across from it to the left, right? So we'll just have one.
So to calculate the number of neighbors, you go 3 carbons away from the hydrogen. So 1, 2, 3. If it hits a hydrogen, that's a neighbor. 1, 2, 3, neighbor. 1, 2, 3, neighbor. So this hydrogen here will have 3 neighbors. 3 neighbors.
Right. Okay.
Right. And if it has 3 neighbors, we do the n+1 rule to show how many suffixes it will have at the HNMR. So it would have 3 plus 1. That's 4 neighbors. So it should have like 1, 2, 3, 4 like that. Right. These 3 hydrogens here will only have 1 neighbor because when we start with one of the hydrogens, 1, 2, 3, it only hits 1 hydrogen. So if it only has,
that would be a quartet.
1 plus 1, 2, doublet.
Oh, okay.
Doublet. Right. This will be a quartet right here.
Right.
Right. This 100 would be a quartet because it has 4 suffixes for the 3 neighbors. But these 2 hydrogens here will be a doublet because it has a 1 neighbor, 1 plus 1, 2, like that. Right. But the integration here would be 3 hydrogens. The integration for this one would be 1 hydrogen, right? Because there's 3 hydrogens there. There's 1 hydrogen here.
Okay, so we get our 3H from how many hydrogens there are from that one?
Yep.
Okay.
Right. And then we see that if there's only 2 unique sets of hydrogens here, we see more than 2 here. We see 1, 2, 3, 4, a lot more there. Right. So that's not the answer.
Right.
So I would go with this one here. But I'm getting kind of confused here because there is like, you see how there's 6 hydrogens here, like that?
Yeah.
Those 6 hydrogens right there are going to be these 6 hydrogens right here on the molecule. 1, 2, 3, 4, 5, 6, because they have the same chemical environment, right? Because we can rotate that bond right there. But we also have, like, I don't see where the 3 hydrogens here are coming from. We also have 9 hydrogens equivalent here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this might be something. CO2. Yeah. So I think this is something else. Like, I don't know. Yeah. So we won't look at this here. I don't know what this is talking about here. That might be a different problem because look at our chemical formula here. We have 2 oxygens in the chemical formula, right, for this unknown compound. But all of these molecules here, they don't have two oxygens. There's no 2 oxygens here.
Right. So are we still able to predict what the molecule is just by looking at what we have?
Yeah, just by looking at this right here, we can still do that. So let me do that with you here. Right. So if I see two oxygens right here, right, and a carbon, this just comes with practice. Like I'm gonna predict this an ester here somewhere because we also have a carbonyl. So I'm gonna draw that carbonyl out like that from the IR. Does that make sense so far? This is the carbon, this is the oxygen. That's the double bond between them.
Yeah.
Right. So now once we have that, I'm gonna put an oxygen right there to show that's the ester right there. Right. Because we have two oxygens in the chemical formula like that. Now I'm gonna draw in the other pieces. You see how here we have 3 hydrogens here? How many neighbors would you expect these 3 hydrogens to have?
Oh, let me see. We would have.
If this a singlet.
It would just have by itself.
Yep. No neighbors. No neighbors.
Right.
Right. And then you know how this is the most de-shielded peak out of all these other peaks right here?
Yeah.
If this is the most de-shielded peak out of all the other peaks right there, then that means that it is going to be the closest to the most electronegative atom oxygen right there. Right, where these 3 hydrogens here have no neighbors. So that's gonna.
Oh, it'll be at the end.
At the end, yeah, with no neighbors, because if you do 1, 2, 3, that's not a hydrogen. So there's no neighbors there. Right.
Right.
Now let's see. We see 3 hydrogens here with 2 neighbors. We see 6 hydrogens here with 0 neighbors. We use that right. Now this is where I just like try random things. There's no 1 hydrogen. So let's see here. 2 hydrogens, 3 neighbors. No. There is a carbonyl. Okay. Is that a broad peak here? 3 hydrogens. Wait, so there's 1, 2, 3, 4. 4 unique peaks. 4 unique peaks. Where 6 hydrogens is one of them. So this 6 hydrogens here is going to be like that with no neighbors.
Right.
So that is going to be 0 neighbors. That's 1 neighbor right there, but we don't have 1 hydrogen. So that has to be blocked by something. It could be blocked by, let's see. You have a carbonyl, 3 hydrogens, 2 neighbors. No, that's not gonna work. Oh, let's see. Let's try this right here. I think this might be a symmetrical molecule somehow. Which is a hard example, but let's see. Or a ring. No, it can't be a ring. It has to be symmetrical. So carbonyl. Boom. 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 But 2 oxygens though. 2 oxygens. And I have 2 carbonyls. So 1, 2, 3. No, 1, 2, 3. So 6, 3 hydrogens with 2 neighbors. It could be like that. 2 hydrogens with, so it could be like that with 4 neighbors. And then this one here could be, let's say, wait, no. 3 neighbors, 3 neighbors, yeah. We'll put a carbonyl right here, and let's put a CH3, but, oh, CH3 right there. This is gonna be 1, 2, 3, 4, 5, 6, 7, 7 carbons, that's good. 14 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 hydrogens, that's good. 2 oxygens, that's good. And we have a carbonyl, that's good. So this is the product that I would be predicting here, but to redraw it, to make it more clean, I'm gonna make the ester like this. This is the carbonyl. That carbonyl is attached to 2 methyl groups going down and ethyl group like that. So this is gonna be the unknown product I have right here. You notice how I just like started trying random things.
Yeah.
Right. Like the reason why I know that this is going to be the right answer is because these three hydrogens right here, notice how that's the three hydrogens that is the most close to the most electronegative atom, oxygen, right here.
Right.
Because those three hydrogens are the closest to the electronegative atom, they're the most de-shielded. They're the most left side right here, which is that peak. So this three hydrogens are those three hydrogens right there. And notice how these three hydrogens only has one subpeak right there. Like
Right.
there's only one singlet. That means that they have zero neighbors. So these three hydrogens here will have zero neighbors. Because if we look at one of the hydrogens, 1, 2, 3, that's a carbon. So that's gonna be zero hydrogens right there. Right?
Right.
And then we see that we have 6 hydrogens, which are equivalent, which are gonna be these 6 hydrogens right here, that have zero neighbors. So when we go down, like let's say 1, 2, 3, zero neighbors for these 6 hydrogens right there, because it's a singlet. And I saw that these two hydrogens right here, you notice how it's a quartet because it has 4 subpeaks right there. 1, 2, 3, 4.
Yeah.
That means it has 3 neighbors because 4 minus 1 is 3, 3 neighbors, right? And those are the two hydrogens right here. These two hydrogens have 3 neighbors, which are these 3 hydrogens right here.
Okay, yeah.
Right. Like, do you get why? Like, there's no neighbors right here.
Yeah, it makes
Right.
sense. It's
Uh-huh.
just I think I would need a lot of practice.
Yeah. This just comes with practice,
Do you
I
think
know.
this is like a typical quiz question though?
A typical quiz question? Not for the first quiz, no. Like you need like the typical first quiz would be like how many neighbors would this set of hydrogens have? What would be the integration? What would be the de-shielded? Like what range would you expect it to be at? Like piecing all those together first, and then like build up to this for the later tests.
Okay, then I'll make sure I'll go over that then.
Yeah, right. It's just a lot of practice. A lot, a lot of practice. I could have broken this down even more to draw out the fragments, but like I just like went by and then the last thing I do is verify, right? Verify with the information you have, the IR, carbonyl, the HNMR, de-shielded peaks, and then the chemical formula and DOU as well. Like with all the puzzle pieces you have, verify.
Okay, thank you.
Yeah, no problem. Right. Okay. So hey Johanna, you wanted to go over the thing you sent me on email? Sorry, for being so late. Like, what time is it over there for you? Is it like 12:43 a.m. right now?
Yeah.
Oh shoot. Like, what, do you have school tomorrow?
Yeah, I've class at 8:30, but I'll be fine.
Okay. That's good. Let me import the document over right here. Let's see. Okay. Let me import this one as well. Okay, add import. Okay, share screen. Share screen right here. Okay. Were you able to try some of the problems, or did you need help with like the whole document?
No, I did most of it. It was just the question from 4 or 5, and with Fisher projections, that's when I was.
Oh yeah, with like the chair confirmation.
Yeah, but mostly with 4 and 5, because his answer key, I had no idea what was going on.
Yeah, so I saw his answer key as well, and then there's like some weird stuff going on. Like this is different than how I learned SN2.
He was explaining class, and everyone was just confused. I didn't understand what was going on at all.
Yeah, I know. Like, does he base his stuff on the textbook, or does he just make up his own stuff in like his own lecture slides?
I don't know what he does at this point.
Yes, because like this right here, like if this is a major product, then that would be the SN2. But like this water here is not a strong nucleophile enough for SN2. This is more for SN1, E1. If you learn it from like most ochem classes or like you watch other YouTube videos, this would be SN1, E1. Which that would not be the major product. Like I think he's doing his own thing here. Right. So
there's like for it to be like SN1, it has to be 50-50 racemic. And then on the other example, it was the same situation, but then he said the opposite.
Yes, I know. And then
Yeah,
this one right here, he's just making it SN2 because this is the major one, and then he's like inverting stereochemistry for some reason. But this is not a strong nucleophile for SN2. This would be SN1.
Yeah, just explain it to me the way you understand it, and then I'll try to go to his office hours.
Yeah, yes. Okay. So the way I understand it, I'm gonna redraw this into a neater form like this. This is the carbon right there. That's the bromine. This is the hydrogen. This is the CH3. This is the CH2, 1, 2, 3, 4. Four of them, 1, 2, 3, 4. This is the CH3 like that. Right. So 4 CH2s, 1, 2, 3, 4, and a CH3 at the end. This substrate right here, the carbon attached to the good leaving group, where this is the good leaving group, is a secondary substrate. Because that carbon there is attached to two other carbons, 1, 2. Because it's attached to two other carbons, it's a secondary substrate. So we have two competing nucleophiles here, which is water and ethanol. So we could actually get a mix of products here. Usually when you have SN1E1, you only get one, either water or alcohol, but he gave you both water and alcohol. So you're gonna get multiple products here, like how I learned it. But based on his thing, he's saying that this is the solvent, but this could have been the nucleophile as well, right? So we know that water and alcohol is a weak base, weak nucleophile, right? So it's a poor base, poor nucleophile. And given the secondary substrate, good leaving group, and weak base, weak nucleophile, this is indicating a big sign for SN1 reaction, solvolysis, right? And A1 is going to be minor, but I'm just going to focus on SN1 here because that's the major product. The very first step of an SN1 mechanism is to kick out the leaving group to form carbocation intermediate, right? But when we form the carbocation intermediate, everything becomes flat and planar, right? There's no more wedge, there's no more dash because this carbon is now sp2 hybridized, flat and planar. So now this is when we get different products here. We can have water attack the carbocation, giving us this intermediate right here. Right? Where because this is a flat bond right here, water could have attacked it on the top side, giving us a wedge product, forcing like one of the groups to be dash, or it could have attacked on the bottom side, giving a dash product, giving the methyl a wedge group. So it's going to give a racemic mixture, like you said earlier. The last step here would be to neutralize and deprotonate that positive charge oxygen by using another water to deprotonate that oxygen by grabbing hydrogen and putting a pair of electrons on the oxygen to make that neutral alcohol right there. So I'm not putting wedges or dashes here because I know that this is a racemic mixture, meaning that there's two products here. This alcohol could have been a wedge, making that methyl a dash, or this alcohol could have been a dash, making this methyl a wedge. So I'm just gonna say racemic right here, right? The other product, because he gave you ethanol, there's gonna be a mix here. Ethanol could have attacked that, and then after we like deprotonate, we could have also gotten this neutral product here. And then there's gonna be O, CH2, CH3, racemic. So we get 4 different products here basically. 2 products here and 2 products here for SN1, right? This he tried to do SN2, but water and alcohol is a poor nucleophile. It cannot do SN2, and that's how I learned it.
Okay, yeah.
Right, but this makes sense, right? Like how you learned it from somewhere else, maybe, or like some other YouTube video.
I understand. I thought it was just 2 products. You said there's 4 products?
Yeah. So are these the 2 products you're thinking of here? 1, 2?
Yeah.
Yeah, those are the 2 products. But you know how I said racemic? The 4 products are like there's 2 enantiomers of this plus 2 enantiomers of that. Like this could have been a wedge, dash, or it could have been the other way, dash OCH2 wedge, like that. Right. Like that's one, that's another one, and then like if you draw out the other enantiomers, that's gonna be 4.
Okay, makes sense.
Right. And the reason why we get a mix here is because you know how this is a flat sp2 carbon. When the water or alcohol attacks, it could attack on the top side or bottom side, giving us a wedge or dash product, like that. Yeah. Okay.
So when he says explain, like, because usually when he gives out his exams, it's usually like explaining why it is. So at the top, he says explain why the major product is dominant, whatever. How
Yes.
explain that? Like, if
Yes.
that was a question.
Yes. So if he tries to do SN2 right here, which this would be the major products because this is the good leaving group right here, bromine, and SN2, we are going to do a backside attack, which does what to the stereochemistry? Does it remain the same stereochemistry? Does it invert or does it randomize?
I'm sorry, were you asking me or?
Yeah. Asking
Sure.
you like, do you know what happens to the stereochemistry of an SN2 reaction?
It's it reverses.
Yeah, reverses, invert stereochemistry. But you see how here this good leaving group here is not a wedge or dash, it's a flat bond. The way that we are going to invert that is that notice how that flat bond is going to the right there. We're going to invert that to the left like that. So when we do SN2, water attacks it, it's going to invert the stereochemistry to the flat bond to the left like that. So instead of inverting a wedge to a dash or a dash to a wedge, we're inverting a right bond to a left bond for SN2. And that's it for that. Did that make sense?
So would that be the same as switching the position of the hydrogen to be on the dash and then the methyl to be on the wedge, or no?
Yeah, so the hydrogen would remain as a wedge, the methyl would remain as a dash, because the bond that we're inverting here is the bond between the substrate carbon and the good leaving group. This bond right here.
Oh,
so we're
okay.
inverting that bond. But this bond is not a wedge, so we can't invert that to a dash. That bond is not a dash, so we can't invert that to a wedge. But it's a flat bond. We can still invert a flat bond where if you imagine an invisible line right here, it's on the right side. So if we invert it, that bond is now going to be at the left side right here.
All right, makes sense.
Right. But if that leaving group was a wedge, then you would have had to draw a dash as the product for the SN2 major. Yeah. Okay. Yeah. So for this next problem right here, this CH3SH, he's saying that the mechanism is SN1. Draw the intermediate in a cyclohexane structure. So, are you familiar with cyclohexanes? Like this? Like these structures
Yeah.
right here?
Somewhat.
Somewhat. Okay. Um, So let's say that we have axial and equatorial bonds. The axial bonds are going to be like this. Start at the leftmost carbon, up, down, up, down, up, down. Equatorial bonds are going to be on the opposite direction as axial bonds. So if we look at this carbon right here, the axial bond is going up. The equatorial one will have to go down then at that carbon. And the direction that it's going to go down to has to be parallel to the second bond. So if you look at this carbon right here, we're going to ignore that first bond, and we're going to look at the second bond right here. It has to be parallel to those bonds, which it is, same direction, like that. Right. So if you look at the next carbon right here, the axial bond is going down, that means the equatorial one will have to go up. But it's going to be parallel to the second bond. So ignore that first bond and look at the second bonds right here. So it has to be parallel to those bonds right there, which is going to go up in that direction, like that. So if you do the same for the other carbons, we would get these equatorial bonds in these directions like that, right? And this is just the chair flip of it, but I'm just going to focus on this first chair right here, where let's say I number this 1, 2, 3, 4, 5, 6. It doesn't matter how you number it. It just, what matters is what you put to it, right? So I'm going to put this as 1, 2, 3, 4, 5, 6, like that, right? So let's say that I have at 1, the ethyl group is going up because it's a wedge. And if we look at carbon 1 right here, the bond that is going up is axial. So my ET is going to be up like this. That's going to be hydrogen at the equatorial. At carbon 2, the thing that's going down is the bromine. So the bromine is going to be down like that. And everything else are hydrogens. And because he said that this is an SN one reaction, the very first step is that the leaving group will leave first. So when that leaves, we're going to have this chair right here, ET, where this carbon will have a positive charge because that carbon lost the bond. Now, when we bring in the nucleophile, CH3SH, it can attach to where the ethyl group is or where the axial group is, right? So have you learned about the concept steric hindrance? Steric hindrance, Johanna?
Yes.
Yeah. Right. So we want the CH3SH group to be opposite from the ET group to avoid steric hindrance. Right. We don't want them bumping into each other. So that's why when the CH3SH attacks this flat carbon right here, there's a preference on where it attacks. It could attack to where like the axial bond is going down or going up the same direction as the ET. Which direction do you think is the CH3SH is going to prefer to go to? This axial bond or this equatorial bond to avoid steric hindrance?
Would it be equatorial because that's the most stable?
Yeah, so that is going to be the most stable position. You're thinking of it like differently, but think of it in relation to the ET, right? You know how the ET is going up? If we look at the equatorial axial here, equatorial in this case is going up as well. So it's going in the same direction as the ET. So if we put the SCH3 here, they're gonna bump into each other like that. Right. Causing steric hindrance. But if we put it in the axial bond, they are anti to each other. Right? They are trans to each other, avoiding steric hindrance. So you're thinking about like the other concept, which is correct. Like equatorial is more stable than axial. But in this case right here, when we're doing SN1, this SH3 prefers to be anti or trans to whatever group that is to avoid steric hindrance. Right. The thing that you were talking about was a different concept. But that's good though. That's good that you're thinking about that. Right. So if the ET is here, the SH3 would go here. And you notice how they're trans to each other. One is up, one is down. That's why this is the major product right here. Right, to avoid steric hindrance. Right.
And then for the Fisher Newman projection, I would just write the Newman projection for the chair conformation. That's the major, right?
Yeah, so for Newman projection right here, let's say this is the ET. We want the SCH3 to be anti to it, to be trans to it. And then let's say this is the bond right there. I don't know how to like draw like a ring like that, but then in Newman projections, what they want to see is that they want to see the ET anti to the SH3 to avoid steric hindrance. The most stable Newman conformer, because it has the least steric hindrance. Right. The hard part here is probably connecting the Newman projection in a ring like that somehow.
Okay, makes sense.
Yeah.
So just a quick question with the reaction, I mean the mechanism being SN1. So it's a DMF, a product solvent. And
Yep, which does not
bromine,
agree with SN1. It should be SN2.
right.
Yeah. Right.
So you agree that the mechanism is SN1, or would you have said it was SN2?
I would have said SN2.
Okay, because that's what
And I would have said this is the major product right here.
All right.
Do you know why though? Like, do you know why I would have said this is a major product? Like, what happens to the stereochemistry here when this nucleophile attacks? Here's what they lead to. Inversion, right? Invert the dash to a wedge. Yeah. But that's good that you're thinking about that. Yeah. Okay. So
thank you so much.
yeah, no problem, no problem. Sorry for making you like wait.
No, you're right. Thank you. Like, I understand better now because it aligns with what I've been like watching, and then when he explains it in class, and then I'm just more confused and
Yeah. Like the way he's teaching it is different than how I learned it as well, and how like I learned it from other YouTubers or like other teachers. So it's interesting for sure. I would ask him about like where he got this from, or like what his thought process on this is.
all right, thank you so much. Have a great one.
Yeah, you too. And let me know, like if you come by again next time, let me know what he says about this. I'm interested.
All right.
Yeah. Good night, Johanna.
Thank you.
Let's see. So I am going to end office hours here. It was a nice 2-hour session. Thank you guys for sticking around. What are you guys planning to do now?
Study.
Study,
Or take
yeah.
notes.
Take notes.
Way's going over alcohols now, so I'll probably show up is it tomorrow? Yeah, tomorrow. Maybe ask about alcohols. I'll submit, or like I'll put under the Google Drive of like her notes.
Right. I see. I think it's best if you do you have a midterm today, Elysia? I mean this week.
I have a quiz.
Oh, you have a quiz this week.
Yeah.
I see. Okay. So, because I'm gonna do all 118A tomorrow, just to 9 to 10 p.m. For farahat and Way's quiz then. Okay. Sounds good. Sounds good.
Well, I mean, I'll still probably like find whatever for farahat's like useful for the finals. So.
Right. Okay. Sounds good. Yeah.
How about you?
I have a midterm tomorrow actually.
Oh yeah, you were talking about it.
I know.
How's the studying going?
It's getting better. I still have to like review a lot of things, so I'm about to do that right now after I like get some water, rest a little bit, and then get studying.
Okay, well, good luck. Good luck on your midterm tomorrow.
Thank you. You too. On your
and thank you so much for the help.
No problem.
See ya.
See ya.